Some of the math we need for physics, we'll need to either review some trig, but we may need to learn some new concepts. So today is probably a new concept for you, but not necessarily. So you're used to things that you measure in science that are quantities like temperature or time or mass. And so these are what we call scalars. So they are just numbers. They have a size, okay? And they also have a magnitude. Usually time is measured in seconds, energy in joules, and we're going to stay in, I should say, MKS units. That means meters, kilograms, seconds, or SI units. And so we have scalars that are given by a size, and then we have vectors, which have a size or magnitude and direction. And so examples of vectors are force, velocity, momentum. So these are physics terms that tell you not only how big something is, but in what direction it points. Probably the easiest first example we'll see is that a scalar is your speed, for example, but a vector would be your speed and then the direction. You're going north by northwest, for example. So we're going to spend some time today on vectors. And a vector, because it has a size and a direction, we can describe it. We often draw it out as an arrow. And so I'm going to draw this arrow as my vector A. And so that's sort of along some line as we go from, say, point here to a point here. A vector is a line that connects these 2 points, but it points along the direction of that line. And we can describe this vector in terms of its component parts. We can think of it in terms of being made up of how far we go along, here's an x and a y axis, how far we go along the x-axis, maybe east, we go some distance like that, the orange distance, and then maybe we go the blue distance in the y direction. And so we describe this A vector as made up of these 2 things. It's added together. In other words, we could walk along the green line, which is sort of the as the crow flies, or if we have to go around the block, we could walk along the red and then the blue to get to the same place. So we would say that vector A is made up of the x part, AX, in the x direction, which is often written as x with a little hat over it. That just tells you it's in the x direction, plus AY in what's called the y hat direction. That is a little y with a hat. And so the hat tells you the direction, and then this little vector over the A you'll see. Now in our book you're going to see, and I will use this notation, instead of x we're going to use I hat plus j hat. So that's another representation, just because we're going to have lots of x's running around, and so we use I hat and j hat to tell us the direction. These are called unit vectors, and they just indicate a direction. It could have been, instead of j hat, we could have used like an n hat to say north, and the I hat we could have used an E hat, for example, to mean east. It's just a way of saying a direction. So A, this vector A, we can think of as being made up of those 2 parts. And this vector doesn't have to be lined up here. Notice here's x and y. The vector is just its length and direction, so you can sort of move it around and say this is also A. It can start here and go to here. Again, it doesn't matter where it's located, it's just telling you how big it is and in what direction it's going. You can go 60 miles an hour north, and you can be in Tampa you can be in Tampa and do that, or you could be up further north on the interstate and do that. Okay, so we want to develop some mathematical skills that we can work with, some tools of working with vectors. And the first one we've already seen is really about adding vectors. We can think of our vectors as being the combination of the paths that you walk. So if we have a series, so we'll say adding vectors. So let's start with vector A again, sort of like this. There's A. And then we want to add it to another vector, say vector B. Then we just take these and we line them up as if we're walking, and it doesn't matter the order. Okay, so we can do A, and then we can add B, which is kind of off in this direction, B, and it's as if we would have walked this direction. This C is now going to be A plus B. You have to be careful because the lengths are not exactly the same. In this case, A and B, I don't know that I've really done them justice, but I tried. A and B are not quite in the same direction, and so only if they're in the same direction will C be then off in be the sum of those. Okay, so let me explain what that means because I didn't say it very well. In other words, if we look back at our vector A, notice that AX, way back up over here, AX plus AY, the value, the length of AX or AY is going to be, if we add those up, not the same as the length of the vector A. So for example, let's start with one, and I won't put it in the first quadrant here. Let's start with a vector that I'm going to draw as vector D, which I'm going to put as -4 in the I hat direction, +3 in the j hat direction. So here we have some numbers. So we go 1, 2, 3, 4 in the negative x direction. Here's x and here's y. And then we're going to go 3 up. So 1, 2, 3. So 1, 2, 3. So right about there. So that's going to be the point I'm aiming for. So that's vector D. Okay, so D is made up of a vector that you could draw as like this and like this. But the length of D, the size of D, we can just use the Pythagorean theorem here, right? Because this is a right triangle, right? So there's a right angle there. So the size of D, which we're going to draw with what looks like absolute values, but this is the magnitude or size of D, is given by, well, the Pythagorean theorem. So D squared would equal this square root of -4 squared plus 3 squared, which turns out to equal 5. So notice the length of this, the size of D is 5 units, but it's made up of two vectors that are 4 and 3 in length, and that's because they're off at different angles. So to generalize this, we can say that a vector A or D, that is AX in the I hat plus some amount in the j hat, that the magnitude of A is given by the square root sum of the square roots. So this is Pythagoras. Okay. As long as we're talking about a vector, though, the thing we said about vectors is that it has a size or magnitude, but also a direction. So looking at this, we've got the size of D, the magnitude is 5. To find the direction, we can ask, what is this angle? And that would give us a direction. Okay? Or we could also ask, what is this angle here, say angle alpha. I'm going to ask what is theta, but you could ask the other question. So if we want a direction, we would say theta degrees, whatever theta is, above the vertical in the negative direction. So this many degrees north, for example, north of west. Right, if this is y, it became north, and this was the west direction. Okay, so to find that angle, we would just say this is 3 and this is 4. Then we can use SOHCAHTOA. We can use our trig expressions. And in particular, if we look at theta and look at 3 and 4, although we also have the length of D, because this is the 3, 4, 5 triangle, that we can say the tangent of theta, right? Tangent, SOHCAHTOA, is opposite over adjacent, is 3 over 4. So we need to find the angle whose tangent is 3 over 4. So this is the arctangent, or on your calculator, tangent of -1 of 3 over 4, and that is 37 degrees. Okay, so this angle right here is 37 degrees. So we can say it's 37 degrees north of west. Or we can recognize that the angle alpha is going to be 180 degrees minus 37 degrees, or 143 degrees. So that's another way to do it. And of course you could get that 143 if instead of using 3 and 4, you put in 3 and -4, right? And you took the arctangent of that. Okay, but it is helpful to draw it out, because sometimes you can get this value, or you can get the other quadrant where tangent is negative, right? Because sine and cosine and tangent are all positive in 2 quadrants and negative in 2 quadrants. So you need to draw it out, really, to see what's going on. Okay, so let's take a different expression. Let's take a different one. So this tells us how we can go from, this is what we call our component form, and then our magnitude and direction. This is magnitude and this is direction. This is the magnitude or size and direction. When you're looking on a speedometer, you don't care about the components, how much east, west I'm going. That doesn't matter. You just want the magnitude and the direction. But sometimes it's useful to have the components. So this is how we start from components and get to, right? Get to magnitude and direction. We're going to go the other direction, where we have a vector. So I'm going to start with a vector down here, just so we can work with it. This is now vector E. We're going to say the magnitude of E is 4, so it's 4 units long. And its angle right here is 30 degrees. So it's negative 30 degrees if you want. 30 degrees below the horizontal, or 30 degrees south of east. So this theta, I'm going to write just as 30 degrees down here. Like that. So now what I want to do from the magnitude and direction is I want to go to components. And so now I have this length is 4, and it's given by 30 degrees. So I'm going to use SOHCAHTOA again. I've got an x, there's EX. I've got a y right here, EY. And if I look at this, then I can say, I've got the 4, which is on the hypotenuse. So I need something with hypotenuse. So let's say that would be SO or CO. So that would be sine of theta and cosine of theta. So sine of theta is opposite. So sine of 30 degrees would be my EY over my magnitude of E. And cosine would be EX over my magnitude of E. So if I put these in, just putting the values in, I have sine of 30 degrees is equal to EY over 4, because that's the value that we have here. And so EY, if we do this, 4 is equal to 4 times sine of 30 degrees, which I think is 2. Okay. And EX, we'll do that one the same way. Cosine of 30 degrees is equal to EX over 4, or EX is equal to 4 times cosine of 30. and that turns out to be 3.46. Now, I have an issue because this EY is in the negative direction. So I can, when I'm writing all this in the components, I would write my E as equal to 3.46 in the I hat direction plus or minus 2 in the negative J hat direction. Or I could write it as, because it doesn't matter where the signs are, minus 2 J hat. And you could have picked up that minus sign by putting in your calculator sign of negative 30 degrees. You would have gotten a negative 2. If you put in a cosine of negative 30, you'd still get a positive value because that's what's going on in this quadrant. Okay, so what I want you to be able to do is use your SOHCAHTOA to be able to get from your magnitude and direction, 3 at 30 degrees, magnitude and direction into components, and be able to go the other way. That is, from component format to find the magnitude using Pythagorean theorem, and direction then using your tangent, or SOHCAHTOA, because you have this, the size of this here is now 5.